Okay, in this class we're going to discuss these questions 56 to 62 on your tuition note. So open your tuition note, keep your tuition copy ready. Okay, tuition copy and then your tuition note that you have with you. Question 56, page 107, tuition note. Okay, 56. So question 56 is, I think, just a matter of reading through it. Look into your note. Light travels fastest in vacuum. Okay, so vacuum is a container in from where you have sucked out all the air. Means an airless container is called that medium is called a vacuum. Okay, in that light travels the fastest around the speed of 3 into 10 to the power 8 meter per second, and in air the speed is only marginally lesser than this, almost the same. So you can write there yes. Okay, the two choices, yes and no, so tick there yes. Okay, next question 57. Let us look there. Question 57, I will read the question. Refractive index in terms of speed of light of two media. So for this, so refractive index, how do you define refractive index? Okay, in terms of the speed of light in two given media. So to understand this, write down on your tuition copy this number and then draw a rectangular glass slab. So this is your glass. Okay, this is glass. This is medium 2, let us say. That means the light ray is going to pass through this only second. Above it is air, and this is medium 1. You draw along with me, okay? Now this is your glass slab, and through this let us pass a light ray. This is called the incident ray, right? Now this incident ray, at this point of incidence, you draw the normal, means a line 90 degrees to the surface of the glass, which is the interface between air and glass. Since it's entering from air to glass, that means from rarer to denser, the ray will bend and go towards the normal like this. Refracted ray will come like this, closer to the normal. So this here is called the angle of incidence, and this is called the angle of refraction, r, small r. Now refractive index in terms of speed of light in the two media will be, refractive index is usually denoted by n. Okay, here see n. And when the light ray enter from medium 1 to 2, the refractive index will be calculated as the refractive index of the second medium 2, with respect to 1. That's why we're writing 2 first. When a ray enter from medium 1 to medium 2, the refractive index that you calculate will be that of the second medium, that is glass, with respect to air. So we write the glass 2 first. This will be given by the speed of this light ray, speed of light, okay, speed of light in medium 1, in the first medium, that is speed of light in medium 1, usually denoted by v1, divided by speed of light in medium 2, that is v2. So when you write the speed of light, the ratio means division of speed of light in medium 1 divided by speed of light in the second medium, that is called the refractive index of the second medium glass with respect to the first. So this is how you define refractive index. So let us look into the note. Let me read the question. I think you have got it now, right? The ratio means division like this. Speed of light divided by speed of light. Ratio means division of same type there. The ratio of speed of light in medium 1, that is usually given as v1, to the speed of light in medium 2, usually denoted by v2, is called refractive index of medium 2 with respect to medium 1. Always medium 2 with medium 1. If the light ray is entering from medium 1 to medium 2, it will be refractive index of medium 2 and not 1, okay, medium 2 with respect to medium 1. That's how you define refractive index in terms of speed of light. Number 58. Look into your note. Conversely, that means the reverse way, the ratio of the speed of light in medium 2, if you do that, divided by speed of light in medium 1, that means if you pass now like this from here to here, instead of medium 1 to 2, you're passing from 2 to 1, then this will become medium 2 with respect to 1. Then this will change, it will become refractive index of medium 1 with respect to second one. So if it is entering from 2 to 1, the refractive index calculated here will be that of medium 1, that is air, with respect to glass. So refractive index is always that of the medium in which the light ray gets refracted, or in which the light ray enters second. Okay. So conversely, the ratio of speed of light in medium 2 to speed of light in medium 1 is called refractive index of medium 1 with respect to medium 2. So if you write speed of light in medium 2 divided by 1, it will be refractive index of medium 1 with respect to 2. If it is speed of light in medium 1 by speed of light in medium 2, it will be refractive index of second medium with respect to first. Okay. I hope you get, so tick there yes. Now 59, go there. Okay, write down on your note 59, question 59. Question 59 there is, what is absolute refractive index? Absolute refractive index. So here, absolute refractive index, let us read once. If medium 1 is vacuum or air, and then the refractive index of medium 2 is considered with respect to vacuum or air. This is called absolute refractive index, or simply refractive index. Okay. So let us say this is if medium 1 is vacuum, that means suppose this is glass. This is a glass and this is medium 2. That means second light ray is going to enter this 1 second, and above it is vacuum, means airless atmosphere, or it can be even air. Then you pass a light ray like this, it will bend towards the normal. In that case, the refractive index of this here, second medium, this is medium 1, that is N2, that is glass. That means you can also write here glass to air, means the refractive index of glass is calculated by comparing with air or vacuum, that is called absolute refractive index. When you calculate the refractive index of any substance like glass or water by passing the light ray first through air or vacuum and letting it enter that medium second, then the refractive index calculated in that manner is called absolute refractive index. Okay, so their formula is like this. Absolute refractive index is Nm, then that will be, okay, so absolute refractive index usually denoted by Nm is speed of light in vacuum, or even it can be air, divided by speed of light in medium, second one, medium 2, in that medium, or you can just write here in that particular medium. It can be glass or water, whatever you're calculating for. Okay, now differentiate between, question 60, differentiate between optically denser and rarer medium. Question 60, let me read it. On comparing two optical media, the one with larger refractive index is optically denser, and the one with smaller refractive index is with larger refractive index is optically denser, and the one with smaller refractive index, it's not complete, write it down, optically rarer. Optically, question number 60. When you compare two media, let us say glass, you're comparing with air or water, then higher, you can write it down, medium, out of these two, the but you cannot do it individually. Optically denser and rarer comes when you compare two. Okay, medium, okay, of higher refractive index, write it down, higher refractive index is called, okay, optically higher refractive index is called optically denser, and the medium of lower refractive index is called optically rarer medium when the two are compared. Okay, so when you compare glass to ear, glass has higher refractive index, it will be optically denser. Ear has lower refractive index, so optically rarer. But when you compare glass with another substance, then glass may become of lower refractive index, then it will become the rarer medium. So it's when you compare any two, which one has higher refractive index among the two is the optically denser, which one has lower refractive index among the two is called optically rarer. So for example, water when compared to glass has higher refractive index, so optically denser, and water has higher refractive index, right? Higher refractive index, so it is optically lower refractive index, so optically rarer. But when you compare water with air, so this is optically rarer when compared to glass. Water is optically rarer. This is important. But when you compare to air has lower refractive index, so optically rarer, and water has higher refractive index, so optically denser. So the same water which is optically rarer when compared to glass is optically denser when compared to air. So it's a optically denser and rarer is a matter of comparing the two given optical medium. And so when it is optically rarer when compared to glass, water is optically denser when compared to air. So it's not a fixed term but relative or comparative term. Okay, so that is question number 60. Now 61. Optical density and mass density are not same. Why? Explain with an example. Mass density and optical density are not same. How can you prove that? Okay, write down question number 61. Important questions. These are all on your text. So question number 61, it says optical density and mass density are not same. You can write down optical and mass density are not same. Why? How can you explain this? That's what the question means. Okay, let us see. Refractive index of indices of kerosene and water are. So let us write here. Refractive index of, let us say, some substances. Refractive index of some substances, kerosene. Okay, kerosene and water. When you compare these two, optical density of kerosene is 1.44, water is 1.33. So water has lower refractive index, so it will be optically rarer and kerosene will be optically denser. But we know that mass density of kerosene is lesser. So here we clearly see that because kerosene is having higher refractive index, it will be optically, we can write it down, denser. And this one will be optically rarer because it has lower refractive index. But mass, right here, but mass density of kerosene is lesser than water. But when you take the mass density of kerosene is much lesser than water. That means if you take 5 liters of kerosene in one bucket and 5 liters of water, same volume on your right hand water and left hand, same volume 5 liter kerosene, you'll always find that water is heavier. That means it has more mass density. But when you consider refractive index, kerosene which has lesser mass density than water, I repeat, kerosene which has lesser mass density than water has higher refractive index. So optically it is denser, but mass wise it is lower mass density. Okay, this explains this question. Optical density and mass density are not same. For example, optical density of kerosene is higher than water, but mass density of water is higher than kerosene. So opposite, right? So that example explains to you why optical and mass density are not the same term or same meaning also. Okay, so here question 62 is a numerical, the last question in this class. This is write down in your note and you can solve it on your tuition copy or even on your tuition note. There is space. Question number 62. This is textbook question, question number 2, textbook page 185, I think. So open your textbook to page 185 or there on your note itself. Light enters from air to glass having refractive index 1.5. So here refractive index of glass, let us say here very clearly it is given to us here. If on your textbook also you'll find it, refractive index of glass. So here refractive index of glass, which is, let us say, N glass to air, so GA, let us say, okay, is equal to 1.5 given. Refractive index of glass is given as 1.50 or means 1.5 only. The next, what is the speed of light in glass? So speed of light in air is given as 3 into 10 to the power 8 meter per second, right? Look there, the speed of light in vacuum is given, sorry, vacuum or air is same. In vacuum here is given as 3 into 10 to the power 8 light in vacuum is given as 3 into 10 to the power 8 meter per second. Now we know that refractive index of glass to air, that means it is entering air first and coming to glass, is always given by speed of light in air or vacuum, so we write your vacuum or air, divided by speed of light in the glass, in the substance whose refractive index we have here, 1.5. So that gives you here, you can write this one, or you can also write like this, okay, this, okay, 1.50 is equal to speed of light in vacuum is 3 into 10 to the power 8 meter per second, divided by speed of light in glass. We don't know that one, we're going to calculate speed of light in glass. Since the light ray is entering from air to glass, the refractive index will be that of the second medium, which is glass. So that's why we wrote G first here. So if you cross multiply this, it will go up and multiply this one, so you'll get 1.5 into speed of light in glass will be equal to, this one is left, 3 into 10 to the power 8 meter per second. So once we're done with that, meter per second, that gives you speed of light in glass, which the question is asking us. Speed of light in glass will be 3 into 10 to the power 8 meter per second divided by, this one will come down, 1.5 will come down. Now decimal in denominator we don't like to deal, so we'll remove. We see one decimal place, so 1 0 means 10, and 10 you multiply up and down. Then you're going to get here equal to, this into 10 is 30 into 10 to the power 8 meter per second divided by, see here, this 0 will go and multiply 3 means 30 into this same 10 to the power 8 meter per second is same divided by this 0 multiply here, then decimal will go one place right, become 15. So 15 2s are 30. So your answer is 2 into 10 to the power 8 meter per second is the speed of light in glass. Okay, so this concludes the class portion, question 56 to 62 of your tuition note. Okay.